For our
Yeah.
listeners, right, could you explain to them what differential privacy means?
Okay. Yeah. So there's a field called computational privacy where you're trying to do a lot of these computational tricks using which you can guarantee privacy to the users who are using some database, or maybe it's their data that's in the database that's being used for some machine learning model, for example. So
Mm-hmm.
within the field of computational privacy, there have been many things in the past, like anonymity and a bunch of techniques in the past, but none of them have been able to capture or give you a guarantee which is mathematical, like a mathematical guarantee of privacy that, I'm able to get zero point 0.5 privacy or 1 privacy in terms of some metric. So that's where differential privacy comes in. Differential privacy is like the golden mathematical worst case guarantee of privacy. So even in the worst case possible, what privacy guarantee can you give me about this model or this pipeline or whatever? So this is still very abstract, but
Mm-hmm.
uh, if you want to go like into like the details of it or to really get an intuitive understanding, imagine that you use a database which say contains Abhinav's data as well, to train an ML model or to get
Right.
or for some query, SQL query, anything. Now, if I were to remove Abhinav's data from this database entirely, I'm going to get a different query output, right? So with Abhinav's data in the database, my query output would be X, and without Abhinav's data, my query output would be X prime. So the how different are X and X prime? If they're vastly different, they might be able to tell us a lot about Abhinav or the person that was missing in the data set, in the second data set. So this is the concept of the differential, that if you remove one person from a database, what effect does that have on the output of the query? And and how can you measure the sensitivity of the query to the difference in the input? And when you get that sort of sensitivity, what does that tell you about who this person was who is missing in the database? So the goal is that somebody who's using an ML model as a black box, they should not be able to tell whose data it was trained on.
Hmm. I
And
see.
so the way to do that is, in this very like differential sort of way that you train a model with Abhinav's data and without Abhinav's data. Can you infer from these two query results that the person who is missing is Abhinav?
I see. And differential privacy deals with techniques to ensure that you have some sort of privacy, that it is your
Yeah.
model training is resilient to such attacks,
Exactly.
essentially.
Yeah. So this
I
attack is called the membership inference attack, which is the
Right.
backbone of differential privacy. And the techniques in DP, in differential privacy, essentially, they are going to adulterate the process. They're going to add noise to maybe the training of the model or to the
Mm,
input
mm,
data or
mm.
some other step in the future. And they're going to do it in the smartest way possible. They're going to add the least amount of noise in the smartest way possible, which gives you a guarantee that you will not be able to distinguish these two distributions of data with and without Abhinav. So, and you can, the best part is you can calibrate how much privacy you want. Do you want like really strong privacy? So your epsilon is 0.001. You want weak privacy, maybe your epsilon is zero point 0.1 or 2 or 3. So that mathematical calibration is really helpful.
So actually, so you use this term, right? The membership inference attack. So can you give a little more example, maybe? So this is essentially that you're using some sort of attack on the machine learning model to
Yeah,
infer about the person whose data is there in the training data, right? So this is one
yeah,
kind
in
of
the
attack.
data set. Yeah.
Yes. So what are the other kinds of attacks which are related to privacy that might be done in a
Okay.
machine learning
Yeah.
context?
Yeah, so one attack is the data reconstruction attack. So till now, we were only trying to figure out, is this person, the membership of a single person in the data, is that person there in the data or not? That's all. But uh, but when it comes to data reconstruction, you're actually trying to reconstruct input data fields. If you're given, say, an incomplete record, this is their age, this is their height, this is their weight. Can you tell me whether they have cancer, whether they have diabetes, whether they have these things? So that is another really important attack, which is the data reconstruction attack, which is like even more like you could have multiple data entries about the same person as well. So it's an even more fine-grained kind of attack.
And how does this happen usually? Do you have some examples or maybe some technique that the attackers would use to do this?
So generally, a lot of these attacks are sort of reverse engineering attacks. They will try to like what they'll try to do is one attack in for data reconstruction is the model inversion attack. So your original model, given an input, it gives you a certain output. Model inversion attack, it tries to create a model where, given an output, you're able to come up with the input for it. So that's
Okay.
like a really big one. Yeah.
I'm kind of wondering. So you said it's a lot like adding noise in order to improve privacy, right?
Yeah.
Uh, but being an ML guy, noise kind of screws up my accuracy, right?
Yeah.
I'd like my data to be as clean as possible. So all of these various methods that you kind of are talking about, like what is their kind of impact um, on the performance of these models?
Right. So naturally, there is a privacy and accuracy trade-off, or more generally speaking,
Mm.
privacy utility trade-off. That the
Okay.
utility of your model does go down, is heavily impacted if you go for like very strong
Okay.
definition of privacy, or you add a lot of noise in the training process.
Mm.
But it is not just so straightforward that if you improve the privacy, the model becomes a worse model. It's not as simple as that. There
Okay.
is the nuance of generalization. So it depends on how well your model is generalizing to begin with. Your model could be a model that's really overfitting, and that's why your accuracy is high. That's why your utility is high. But in the truest sense, then that is not the model that you're looking for. So in some
Mhm.
cases, this has actually been observed that when you do add privacy, you add privacy noise to the process of the training of a model. Even though your accuracy during training might go down, it actually helps improve generalization. So it can give you a boost in the final utility of the model.
Sure.
And these things, empirically, they're hard to, always emulate correctly. But
Mhm.
there are theoretical proofs which show that privacy does support generalization of ML models. And so it's kind of like thinking about the robustness of machine learning models. You're trying to
Mhm.
make your ML model robust to all sorts of attacks. So privacy just
Right.
falls within the purview of those set of attacks that you would want to be robust to.
Right. Right.
Makes sense. Makes sense. Actually, so we have this thing, which is kind of, I can kind of put it in a different context where there is this dropout mechanism in neural networks, right? Which is
Yeah.
also essentially kind of a noise mechanism, and that ends up improving the generalization. So what you're saying is
Yeah.
a lot like that. At least that's how I kind of contextualize it.
Yeah, I mean, that's
So
a really good observation because there is an inherent privacy that you get with Dropout. So
Mm.
there's a paper
Mm.
which talks about the privacy that you get for free because of Dropout or
I see.
L2 regularization and things like
Okay.
that. And a few transformations also, the Johnson Linden Strauss transformation and things like that,
I see.
that give you privacy for free. So yeah, there is like good theoretical work on that.
So basically, there's a
Interesting.
correlation between the generalization of the model with the privacy that it inherently has.
Yeah,
If
yeah. But
I'm
it's
hearing it
really
right.
hard to show this in experiments because training is very like non-deterministic stochastic.
Mm.
So unless
Right.
you're working with huge hyperparameter sweeps, it can be pretty hard to
Mm.
Right.
show
Right.
these results that, there's this direct correlation. Yeah,
Right.
Mm.
So this
yeah.
is
Right.
actually the one thing that I wanted to touch upon here,
Sorry.
right? Because go
Yeah.
ahead, sorry.
Yeah, no, no, I was just thinking, so this correlation that you're talking about, is it like this generalization and improving this whole thing with privacy? Um, is it specific to the kind of ML model? Because certain kinds of models by themselves are very hard to train, right? Like generative models, like a lot of GANs and stuff like that, they are really, really tough to train. And I don't know, like, yeah, exactly. So how does this whole privacy, is it specific to maybe certain kinds of models?
Um, so conceptually, it should hold true for many models, for many classes of models. But like you said, the reality is that some models are much, much harder to train than others.
Hmm.
There, I'm not really sure about the result
Okay.
in terms of privacy
Okay.
and generalization. But one thing that is definitely non-trivial is that for any kind of ML model that you work with, uh, different classes, different mechanisms, different algorithms, the way you come up with the private version of that algorithm, that is non-trivial. So you really have to kind of do the work of coming up with a privacy mechanism and proving that it actually gives you
Hmm.
this guarantee. So that is the part which is not like very easy to automate. You can't just uh, you
Okay.
can't just like make a computer to do that, for
Got
example.
it.
That is something that
Got
can be
it.
tricky. So but one work that did come out in that, in to improve that, was like DP versions of, or private versions of optimizers. So no matter which
Okay.
class of ML algorithm you're training, you're going to use one of these basic optimizers, SGD, Adam,
Right.
whatever. So they have private versions of those optimizers. So that was like a really big deal in the privacy community, that they came up with DPSGD, DP Adam. Yeah.
Got
Yeah,
it. Got it.
this is
One
actually
thing I want to
interesting.
understand is use. So sorry, I'm completely like, at least Devan watched the video. I have no idea, so I have a ton of questions. Privacy. You said there is certain kind of guarantee that you can actually give. So what do you mean by guarantee? Like, how is it exactly quantified?